Welcome to Lecture 11 and GRA 6036. Today is the 2nd of April. And today we'll be working with project 14. So soon we'll sit ready and you can post your questions to project 14 under questions video on YouTube. And we'll answer them in the comments section. Today I've also written a lecture note. So the lecture note is out, so you can find it here. And so this note is about regression models and also about the assumptions we're making and what can go wrong when we do regressions and how to see if things go wrong. So in this script I've simulated regression data, so that means that we know the truth, so we can fix things so that things are correct and that things are wrong, and we can then assess how our methods and estimation methods work when things deviate from what we assume. So you should read this note carefully and also work through the R script that I use to make these figures and estimators and so on. So the R script will soon be out. It's this R script right here. So, but since I use a lot of simulation in this R script, I want you to know about some standard simulation methods. And so I want you to know the R norm function. You've probably seen all these functions before, but here's so we are going to talk about R norm function, the R binom function, the runif function, and sample. Okay, so I hope to get through this in a reasonable amount of time. So these are all functions to simulate data. And simulate data means basically that, well, we have an extremely big hat with many tickets in the hat, and we just draw a random number of tickets out of this hat, and the probability for which we pick each ticket is specified by the distribution. So normal, binomial, uniform, and we'll also talk about this sample function, which is a bit different. Well, anyway, so let's be more concrete. So with the R norm function, R norm, it says random normals. Then you have to specify how many of these you want to draw. So let's say we draw 10 random numbers from a normal distribution. And then we could also, I mean, in R there is if you just write this, you'll get 10 random numbers from a normal distribution with mean 0 and variance 1, because that's the default in R. I like to specify, since I like to specify, and so that it's even easier to see that we are actually drawing from a distribution with mean 0 and variance 1 in this case. So we could do mean 0 and standard deviation 1. So this means that these numbers, when you draw these, they will on average be 0. So they will not each individually be 0, as you can see, but on average they will be 0, and their variance will be, or the standard deviation will be 1. So when we simulate these numbers, we might put them into a vector. Let's call it vector x, or maybe y will be more better since we are going to work with regression. So we put this into y, and then we can have a look at y, and we see, well, here are 10 random numbers. So if I do it one more time, I get 10 different numbers. Okay, but what they all have in common is that they come from a distribution where on average a draw is equal to 0, and where the spread is described by the standard deviation, that is 1. So you can then take the mean of the y and the standard deviation of the y. So these are empirical things. We know that if we had infinitely many, this mean and the standard deviation would be 0 and 1 respectively. but they will not be when we only have 10 draws. They might be, I mean, as you can see, they are close. And we can expect to get closer if we increase the sample size. So let's increase it dramatically to 1000 and do this one more time. And we see that, well, we are closer to the true values. So if you increase it even further, you'll get even closer and so on. But it's not, not monotonically, of course, because there is randomness involved. So when we have these, so now we've drawn some 1000 random normally distributed y's. So we could make a histogram of these y's. So we know what this should look like. Here it is. So that's that's how a histogram, if you really have normally distributed data, this is what a histogram you'll expect a histogram to look like. Something you seldom see in reality, of course. And now we could add this bell curve that you know to the histogram to see how the histogram nicely, or the bell curve will nicely trace this histogram. So here's code for this. You could do curve d norm x 0 mean 0 standard deviation 1. So d norm, the d norm function is then, well, is a normal density. So that's just a function drawing a curve, and this curve thing says, well, draw this function to some plot that is open. So here we have a plot that is open, and we want to add this curve to this plot. So we say add true, and then let's color it green. So now we add this curve, and we see, well, you know, the histogram and the true density that we drew from fit quite nicely together. But you could also, I mean, you could also increase the, so I mean, these data, now they had variance 1, we can increase the variance and see what happens. So then we can double the standard deviation and draw these once again, and we see, well, the standard deviation is, our estimate of it, or the empirical thing is, it's close to 2, which it's supposed to be. And we could draw the histogram once more. So now we see that they're more spread out. You can see that the x-axis have changed. And now we can add this curve where we adjust for more noise. And this curve fits nicely. So if we add the curve from that we had, the one with standard deviation 1, you'll see that that curve is now too tight because we have more variation in our data. So now we're just playing around and simulating data, but there is something to learn from it, because when we have data, we make histograms and we plot the data, we look at it, and we wanted to have certain features, but it's not always easy to know what would be perfect data. But you know, when you simulate data, we know what perfect data. We know that these are perfect normally distributed data, and then we can have a look at it, what it would look at in the ideal case. Okay, so let's jump to the R binom function. So the R binom function is also a way of drawing random numbers. It's basically a function for doing random coin flips. So first you say how many experiments you want to conduct. Then you say, well, each experiment should consist of how many coin flips. So either 1 coin flip in each experiment, each experiment is 2 coin flips, or 3 coin flips, or each experiment is 100 coin flips. But let's do that. We are doing 10 experiments, and each experiment consists of 1 coin flip. Then you have to indicate the probability of getting heads or tails. So we'll here simulate data from a perfectly fair coin. If you run this, you get 0s and 1s. So these are then the tails and the heads, if you want. So we could then do more of this. So let's do 1000. And we can save these into a vector. So then x is 1000 coin flips. Now you could take the mean of x, and what that we would expect to be, well, 1/2. And as we can see, it's very close to 1/2. If we do this again, we'll get a different number that is also close to 1/2. So what happens if we say, okay, now I want to do 10 experiments with 2 coin flips in each? Then we'll get a vector that counts the number of let's say heads in each experiment. So in the first one, we flipped the coin 2 times, and we got we got 1 head and 1 tails. Same here, 1 head and 1 tails. No heads, 1 head and no tails. 2 heads, 1 head and no tails. 2 heads. Okay, so the same if we increase this to 13. We'll get a number of heads in each experiment. And each experiment now consists of tossing a coin 13 times. Okay, so I'll stop this video here, and in the next one I'll talk about the runif and the sample functions, and then we'll proceed to the notes that my pre-written notes.